Dear students, we are going to our third chapter, that is bounded operators and adjoints. We know what is an inner product. What is an inner product on a space X? Inner product on X is nothing but a function which assigns a scalar value. This is known as read it as inner product xy for all x comma y following x. That's a function. Then we know the properties of inner product. Inner product, that is the linearity to the first variable, linearity to the second variable, and inner product kxy is k into inner product xy, and so on. Moreover, what is the relation between inner product and norm? We know that norm x equals square root of inner product xx. And moreover, inner product xx equals 0 if and only if x equals 0. Okay. Now, if x and y are any two inner product spaces, x and y are any two inner product spaces, then that it is the inner product defined on x cross y. Inner product defined on x cross y is, consider this inner product xy1, inner product x1 y1 x2 y2. Inner product x1 y1 x2 y2 equals this inner product x1 x2 plus inner product y1 y2. This is the inner product defined on two inner product spaces x cross y. Agreed. If x and y are into inner product spaces, then the inner product defined on x cross y is inner product x1 y1 x2 y2 is inner product x1 x2 plus inner product y1 y2. Now, what is norm AX? You know that what is norm AX? Norm AX. This is norm AX is if A is bounded. Suppose A is an operator on X. Then A is an operator on X. A is bounded means norm AX less than or equals alpha into some alpha into norm X. Where X is in X for all X following X. And alpha is, so that some alpha is positive such that norm x less than or equals alpha x. So, further norm ax is defined as norm ax. What is norm ax? We know that it is supremum. Norm ax equals supremum modulus of inner product axy, where y following x with a norm y less than or equals 1, with a y following x with a norm x less than or equals 1. So this is inner norm ax. Norm ax equals supremum modulus of inner product xy for all y following x with a norm y less norm y less than or equals 1. So that means modulus of inner product axy, modulus of inner product xy, so which is less than or equals norm ax into norm y. Okay, modulus of inner product xy less than or equals norm x into norm y. So this implies what is norm A? Thus norm A equals supremum modulus of inner product axy for all x comma y following x with a norm x less than or equals 1 and norm y less than or equals 1. So these are the two important definitions or two important results. Norm ax equals supremum modulus of inner product xy for all y following x with a norm y less than or equals 1. And the norm A equals supremum modulus of inner product xy for all x comma y following x with a norm x less than or equals 1 and the norm y less than or equals 1. Agreed. And also we know that what is a Banach space. Banach space is a complete complete normed space. Here, another is Hilbert space. What is Hilbert space? Hilbert space is X is Hilbert space. Hilbert space means it is a complete inner product space. Hilbert space is a complete inner product space. So in this chapter, we deals with the properties of adjoint operators. What is an adjoint operators? and its properties. So, first we are going to a theorem. The theorem states that let H be a Hilbert space. H be a Hilbert space. That is, H be a complete inner product space. A is in BLH. A is a bounded linear operator on H. Then there exists a unique B following BLH. The uniqueness is preserved. Unique B following BLH such that inner product AXY equals inner product XBY. Inner product AXY equals inner product XBY for all x, y following H. So this is an important theorem. Why? Because from here we define what is the adjoint of A. So H be a Hilbert space. It's a complete inner product space. A is in BLH. A is a bounded linear operator on H. Then there exists a unique B following BLH. The uniqueness of B is preserved there. Unique B following BLH such that inner product AXY equals inner product XBY for all x, y following H. How to prove? So its proof is let y following H. Y is an element in H. Now we define a function Fy from H to K. H to K by Fy of x. Fy of x equals inner product AXY. Define a function, define Fy from H to K by Fy of x equals inner product AXY, where x is again in H. Clearly Fy is linear. That's a linear function. Why? Because inner product is linear. So clearly this Fy is also Fy of x plus y or x plus h. Since inner product is linear, surely Fy is linear. So yes, Fy is a linear functional. Fy is linear functional and modulus of Fy of x. What is modulus of Fy of x? Which is equals modulus of inner product AXY. Modulus of inner product AXY. So which is less than or equals norm x into norm y. Norm x into norm y. So which is less than or equals norm x means norm a into norm x into norm y. For each x following x, y following h, norm x and norm y less than or equals 1. So finally norm Fy of x, that means modulus of Fy or norm Fy less than or equals norm a into norm y. Fy of x. So norm Fy less than or equals norm a into norm y. Further, Fy is a linear functional. Fy is a linear functional. So for all x following h, Fy is bounded means Fy is continuous. Okay? Fy is a linear functional. Norm Fy less than or equals norm a into norm y. So for all x following h, this Fy is continuous. So this implies Fy is continuous. Okay, Fy is continuous. Then by Riesz representation theorem, we know what is a Riesz representation theorem. That's a well-known result. Here, Riesz representation theorem says that when H be a Hilbert space and F following H dash, dual of H, F following H dash, then there exists a unique set following unique y following H, unique y following H, such that F of x equals inner product xy. This is the Riesz representation theorem. H be a Hilbert space. Here again H is a Hilbert space. F is in H dash. H dash means it is a dual. F following dual of H. F is a linear functional. Then there exists a unique y following H with F of x equals inner product xy. So all of the conditions of Riesz representation theorem satisfies here. Fy is a linear functional on H, which is a continuous. H is a Hilbert space. So hence by a Riesz representation theorem, there exists some set following edge such that Fy of x equals inner product Fy of x equals inner product xh. F of x equals inner product xy, like this. By Rees representation theorem, there exists unique set following edge such that Fy of x equals inner product xh. Now we define this b of y equals h. Define b of y equals h. This set is defined as some b of y. Then clearly this b is an operator on, where b is an operator on h. Okay. Therefore, here we get Fy of x equals inner product axy. Moreover, Fy of x equals inner product xz. So we can conclude that here Fy of x equals inner product axy, that equals, but or inner product xy equals Fy of x, it is defined. But this Fy of x equals inner product xz. But we know that what is z equals b of y, so it is inner product x b of y. So finally we have that is inner product axy equals inner product xby. Inner product axy equals inner product xby. Then this is what we actually require. Inner product xy equals inner product xby, where b is a operator on h. Then next we want to show the uniqueness of b. If possible, there exists some b1 which also satisfies this condition. That is inner product axy equals inner product xb1y. So from here these are equals. So what do you get? Inner product xby equals inner product x b1y. That equals inner product x b minus b1 of y equals 0. Then this is possible only when, since x and y are differs from 0, b1 minus b equals 0 or b equals b1. So the uniqueness of b is again preserved. Okay, so this is actually what we require. So now we are again goes to this theorem, that is when H be a Hilbert space, A is in BLH, then there exists a unique B for an H with a inner product xy same as inner product xby. Here, if then this B is an operator on H, A is again a linear operator, then this B is said to be the adjoint of A. B is said to be the adjoint of A, that is B. This adjoint of A is usually denoted by A star. A star equals B. Adjoint of A, that is denoted by A star equals B. Therefore, this result becomes inner product AXY equals inner product X A star Y. So this A star is known as the adjoint of A, and this is one of the important results. When A is in BLH, then there exists A star such that inner product AXY equals inner product X A star Y. Consider this relation. Inner product AXY equals inner product X A star Y. This A star is known as the adjoint of E. Okay.